Hi everyone, thanks for staying for the last talk of the day. My name is Ryan Little. I'm a PhD student at Boston University. Today I'm excited to share some work with my co-authors, Lucy Chin and Mayank Varia. And just as a quick disclaimer, there'll be some brief discussion of sexual assault in this talk in the first slide, and the rest of the talk will be just technical. So I'm going to start with our motivation. So for the past couple of years, myself and my co-authors have been working with a nonprofit organization called Callisto, which provides services for survivors of sexual assault. And so Callisto, because of the strong privacy needs of these users, Callisto strives to not store any personal information. So no usernames, no email addresses, no phone numbers. And so this strong privacy need has required them to do some interesting things, to do features that are common on websites. So for instance, they have to do an oblivious login system to avoid storing usernames and passwords. And so today I'm going to talk to you about how we solved a similar issue, namely the problem of account recovery. So if a user for the service forgets their password, how can they come back and then regain access to the account without the server having to store information about them? So this work culminated in a protocol which is currently which has been implemented by their engineers, and it's currently running live in production on their website, projectcallisto.org. And though our protocol was designed for Callisto's specific use case, it's a general protocol that can work for any other website. So let me talk to you about the problem of account recovery. So this is a very standard feature in websites. I think we're all familiar with it. The idea is that when you create your account, you're going to choose some set of security questions. And then later on down the line, once you've forgotten your password, you're going to navigate to a page where you enter your email address associated with your account. Once you do that, the service will send you an email containing a one-time link. If you click on that link, you're then brought to a page where you're prompted with those security questions. And if you answer those right, then you can reset your password, regain access to your account. OK, this is a user experience that's very familiar, and it works pretty well. But the problem for us is that it's typically not done privately. So on the back end, the server will just store a list of usernames and email addresses and security questions for each of the users. So this doesn't work for our use case. So what I'm going to show you today is a new account recovery protocol, which follows, from the user's perspective, is going to follow that same user experience. But behind the scenes on the server doesn't need to store any identifiable user information. And because this is a protocol for real-world use, it's fast in practice, and it uses only lightweight cryptographic primitives that can run in a web browser. So let me tell you about our setting. So we're modeling the server as breaking up into n different recovery servers, each of which is owned by a different Callisto worker. And then we have a client on the bottom here. And then the security goal that we're trying to achieve is that an adversary shouldn't be able to learn a list of users, usernames or email addresses of the users of the system. And then one crucial attack that we're looking at in this talk is dictionary attacks. So if the adversary has some big list of email addresses or phone numbers, they can run a dictionary attack where they just go one by one through that list and try to see who is in the system, who is not. So we have a single protocol, but we look at it under 3 different threat models, and we get different security properties in each of these threat models. So the first one is an external adversary. This is where each of our recovery servers are semi-honest and non-colluding, and we have a malicious client on the bottom who is trying to just probe the system and learn information about the users. So this is our weakest threat model, but we get the strongest possible security here, which is the adversary cannot learn anything about the users. We also look at an internal adversary. And so here we have up to n-1 of the recovery servers are corrupted, and they may be colluding. The client here is also malicious, and they may all be colluding together. And so in this threat model, it actually becomes possible for the adversary to run a dictionary attack. They'd have to guess both the user's email address and the phone number together. But if they can do that, then they can learn if they're in the system. We're actually able to prove that the dictionary attack is the strongest possible attack on the system in this threat model. And furthermore, we can kind of mitigate the dictionary attack by having some rate limiting. So the one honest server can impose some kind of rate limiting to slow down or stop any kind of dictionary attack that's going on. So now here, this is an MPC session, so maybe you're thinking, maybe the solution here is just use MPC. So one approach to do this would be we could just have the client secret share her personal information, store it on the servers, and the servers could just run account recovery in MPC. This would work for the two-throw models I've introduced before, but the problem is that if all the servers were to collude, they could just trivially reconstruct all those shares and learn the entire list of user information. And we actually want a stronger notion of security than that. So we capture this stronger security with the notion of a compelled adversary. And this is less commonly seen in the MPC literature, but we define this as now all the parties are malicious, and they're all colluding, and they're all working together. So this is actually motivated by a concern that Callisto has, which is that at some point a court might issue a subpoena against them, asking them to disclose the whole list of their users. Callisto wants to still maintain user privacy even in this very strong case. So once you have a compelled adversary, rate limiting is now not possible because there's no more honest party who can do rate limiting. But we still get the guarantee that the best possible attack here is a dictionary attack. And so what this means is that you would still have to spend a considerable amount of time and money to run this attack. And so even if you were to throw away the non-collusion assumption, you still get some meaningful privacy guarantee with our protocol. So let me tell you about a core building block for our protocol. This is called an oblivious pseudorandom function, or an OPRF. This is an interactive protocol between two parties, a client and a server. And the idea here is that the client gets to pick some secret input for a PRF and then learn the output of that PRF on their secret input, with the server learning nothing. So we like OPRFs for a couple reasons. First of all, they're very fast in practice, and they're also very easy to code. So this is important for us because we're working with a nonprofit, not a big tech company. They have limited resources to build this, so we can't ask them to build anything that would require too much manpower. We also like this because Callisto's actually already built this. So Callisto already uses this for their login system and also some other parts of their system. So quickly, at a high level, how we use OPRFs for our system is during account creation, the client on the left is going to do an OPRF procedure with each of the servers. And her input for each of these is the same. It's her email address and her phone number together. So she does this, and she gets back n different pseudo-random outputs, y1, y2, and y3. She's now going to take those outputs and then hash them together with some slow hash function to produce two values, an ID string and then a key for a symmetric encryption scheme. So under this key, she's now going to encrypt her contact information and then her chosen security questions. Then she'll send that ID and the ciphertext to the servers to be stored. And so the servers at this point can't learn anything about the ciphertext because they don't know anything about the key. They've learned nothing from these OPRF interactions, so they have no information at this point. Okay, so now let's say we're now in the future. The client has now forgotten her password. We assume that she's lost basically all her state. So we assume she has no more keys, she has no ciphertext, but we do assume that she still remembers that email address and that phone number that she used to create the account. And so those two things are actually all she needs to do to rederive that same key. So during account recovery, she's going to redo these OPRF interactions with the same inputs, get back the same outputs, and then derive the same key again. But this time, she's actually going to just send that key to the servers. The servers can then look up the ciphertext and then decrypt it, learn the user's contact information to send that email with a one-time link. So there is actually leakage happening here. But what's happening is that the server can send that email and then they can just erase that information. And so the servers don't need to store that information long term. So this slide is only showing part of our recovery system. Once the user gets that email, they then have to answer their security questions. And then to do that, it's essentially the same idea, but this time they're going to send the answers to the security questions as inputs to an OPRF, get back different values, and then use that to derive a key. So there's one issue with this protocol that I want to address, which is that we want to rate limit account recovery to stop these dictionary attacks, but we also don't want to rate limit account creation, because if Callisto were to do a promo event or something and a bunch of people were to sign up for the system, we don't want to turn away honest users from signing up for the service. And it actually becomes tough to rate limit these two use cases, account creation and account recovery, separately if we're using OPRF. Because any kind of account, or any kind of rate limiting that you put in account recovery, an adversary can just bypass that by doing the same OPRF queries during account creation. So we solve this by introducing a new primitive, a new variant of an OPRF, and we call this primitive the K-pop, the kaleidoscopic partially oblivious PRF. So K-pops are a primitive that can operate in two different modes. One is OPRF mode. In this case, they work just like an OPRF. They can also run in POPRF mode, which is partially oblivious PRF. And so here, the input to the PRF is now split into two halves. One half is secret, and one half is public. One half is known to both parties. And then crucially, in a K-pop, both the OPRF mode and the POPRF mode is computing the same underlying PRF. So we can put this into our protocol by, just quickly, I'll go through it. We can just swap out the OPRF with the K-pop. And the broad idea is that during account creation, we can run it in one mode, in POPRF mode. And then during account recovery, we can run it in OPRF mode. And so now the service can impose rate limiting by just rate limiting the number of K-pop interactions that they're willing to do in OPRF mode. And so I will direct you to the full paper for much more. We have a full construction. We have an open source implementation of our K-pop, as well as benchmarks in the paper. We have two security proofs. One is in the UC framework. One is in a more easy to understand game-based framework. And there's much more. And with that, I'm happy to answer any questions. Thank you.